Well, hello, good afternoon to everybody. I am Angel Conde from Netherlands, and I'm here to present a joint work with ULMA handling systems. I'm going to talk about how to solve Industry 4.0 challenges using Apache MESOS, specifically in the logistics domain. I have divided this talk in 4 main parts. First, I will give an introduction about ULMA handling and the Industry 4.0. Then I will talk about the components that we have chosen for the solution. Next, I will talk about the architecture. And finally, I will give some brief conclusions and future work. Well, ULMA handling systems provides all-round logistics systems. For example, in this case, automatic warehouses. It focuses on custom turnkey solutions where it carries out the design, the assembly, development, and maintenance. And moreover, ULMA handling has worldwide presence. Well, let's see what is an ULMA warehouse. In this case, in this picture, you can see a beverage warehouse. And what a warehouse, in this case, is composed by different elements, for example, stacker cranes, conveyors, elevators. And we can say that it's a system that is physically distributed, composed by independent devices that carry out automatic tasks. Well, the problem with automatic elements is that they fail sooner or later. For example, in this case, they can fail physically with deterioration or failures, or we can have different logical failures, like software errors, software updates. In this case, we have the logical-physical world mismatch. That's it. A human being can move one thing from the warehouse to another part where the software doesn't know where it is, and it fails. Well, after some time, the Industry 4.0 relating to cloud, big data, industrial Internet of Things, cybersecurity, machine-to-machine, the concept has arisen a lot nowadays, and ULMA started to think, well, I would like to reduce the downtime of my warehouses. I would like to have more integration with third-party systems. I would also like to lower the maintenance costs, doing predictive maintenance, and to conclusion, I would like to have a smart warehouse. With that in mind, ULMA built the supervisor. The supervisor gathers information about operational data and malfunctions from the warehouse. The supervisor gathers information from, for example, the conveyors, the elevators, using a message bus called DTS. And we employ also the format of the data, and IC 61850 in the standard that is based on electronical substations, but we think it's quite good for this kind of information. We can say that the supervisor is distributed because the system is distributed by its nature. It's scalable because it works with different sizes of warehouses. It's extendable. We can use it with different devices, and it should work without errors. Well, after applying the supervisor to different warehouses, ULMA realizes that it was useful for local maintenance, and its data was valuable for later analytics. However, we couldn't do with the supervisor remote monitoring. The data collection was manual, and the operational data can be lost. Therefore, we have developed the Cloud Supervisor concept. The Cloud Supervisor is a live mirror, live stateful mirror of each real supervisor in each of the warehouses, and is responsible of storing the operational data in a safe manner in the cloud. Also, the Cloud Supervisor is stateful because it can define its own rules. That's it. And Cloud Supervisor can define a rule that I don't want to save this information this operational data that is going inside me because I don't care about it. or it can generate more operational data from the rule engine. Moreover, we would like to have aggregate support. That is, a cloud supervisor can represent data from one or more supervisors, real supervisors, from different warehouses. Well, this leads us to the point that we need to run this cloud platform. We need a platform, and let's talk about the different components now. Well, our platform should achieve some goals, or we have some requisites, or how do you want to talk it? We would like to have a platform that can run in a public cloud, private cloud, hybrid cloud, wherever. We would like to have a platform that avoids vendor lock-in, that is resilient and elastic, and it should provide efficient resource usage, because if not, the usage cost will be higher and you will not be competitive. This leads to the point of choosing Apache MESOS. Why MESOS? All of this thing goes through the point of going from static resource partitioning to elastic sharing. That's it. In the left part of the image, we have the static partitioning, where we have some servers assigned to analytics, some of them to databases, and some of them are doing services. Using Apache MESOS, in the right part, we can assign to one server, like I want to have 4 CPUs for Spark. I want to assign 2 CPUs to Cassandra, and for the services, the rest. And moreover, we choose MESOS because there are a lot of internet guys, big guys, that are using it. Well, let's start with a small overview of MESOS. In MESOS, you have the different distributed resources. You have your CPUs, GPUs, your memory, your physical resources. Then you will usually have a distributed file system where your files or programs configuration are. And then you have the MESOS kernel. The MESOS kernel, you can interact it with different languages, such as Java, C++, etc. And in top of that, you will have different frameworks that will be responsible of your running apps and services. Well, let's go through MESOS features. MESOS was battle tested on Twitter. Its scalability has been proven up to 10,000 nodes. And both 2 points that are important for us is that we can launch any task using Docker or Citrus containers. Moreover, we have resource isolation. That's it. We can have a web service that we can assign it 0.1 CPUs and 60 megabytes of RAM because it's doing nothing. And an important point from the industry is that you can have commercial support from DCOs, the guys from MESOS. Well, but how do you build this platform? You start to launch virtual machines, EC2 machines on Amazon. Then you go to the secure cell and start to install things, etc. Wow, no way. We have applied a concept called infrastructure as a code in this project. First, using Terraform from HashiCorp, we do some scripts, and we can launch the platform on any cloud provider. And in case you can launch in your own premises too, using OpenStack. We use also Ansible for provisioning the machines. That is, we can install the software configuration and automate updates and upgrades with this tool. Well, let's start a brief building blocks of the platform, the general blocks in these kind of platforms. You usually have the data ingestion and message bus part in the bottom. Then you usually have data storage. Can have Hadoop or Cassandra or whatever you like. Then you usually have also a building block of analytics, real-time, batch, machine learning, etc. And you finally will have a part of visualization and user experience. This is the part where the cloud supervisor will be. And the last part, you have the infrastructure where the platform will run. In here, Amazon, Azure, Google Cloud. We don't care. Well, Let's start with the first component, or the reverse proxy. We have used Traffic, modern reverse proxy writing in Go. The important thing about Traffic is that it has dynamic watchers for backends. That's it. If you launch a new task on Mesos, you can assign dynamically a new entry point for that task. Well, Traffic is open source. It can terminate HTTPS traffic. We have deployed it on the so-called Edge node. Well, the next one, the message bus. Well, Apache Kafka. We use it in order to deploy the couple, the components. We have chosen it because it's de facto standard in big data architectures. It has a publish subscriber model, and it's reliable. Its performance is very high. And we have deployed it in this platform using the MESOS framework. Well, let's talk about the storage. For this project, we have chosen to deploy the Hadoop file system. We have installed it in the Mesos master nodes for this project. We have also chosen the Parquet command format in order to speed up the queries. We didn't deploy it as Mesos framework because we don't think it is quite in production level yet. Well, Hadoop, in this case, gives us horizontal scalability. And the bad thing about Hadoop is that we have to deal with the small files problem. We will talk about that more later. Well, about analytics. For this platform, for this solution, we have chosen Spark. We have chosen mainly Spark because it's analytics in memory and because you can have standard SQL support for your data scientists. We have deployed it using the corresponding Mesos Spark scheduler, and we can apply. The important thing here is that we can do machine learning and real-time processing with it. Well, in all of these kind of platforms where you can run different workloads and in different nodes, you need always a service discovery tool. In this case, we have chosen Consul. Using Consul, we can do service discovery using DNS records, and the port discovery, we can do it using SBR records. We also use Consul to do service health monitoring. For example, you have in the image that we are checking the Zookeeper service and the Mesos service. And for registration the task in Consul, we use a tool called Marathon Consul. That is, when you launch a task in Mesos or Marathon, you will get automatically created a DNS entry for that task. Well, in this figure, we can see a platform overview where the incoming traffic goes secure with HTTPS, and then go to the Edge node, and the Edge node do the traffic ingestion and terminates the HTTPS. Then we have the Mesos master nodes. The Mesos master nodes do the coordination in Mesos. We have there also deployed the HTTPS name nodes and the Consul servers for the service discovery. Finally, we have the agent nodes where the Mesos agents lives, where we will have the HTTPS data nodes, the Consul clients, where the different tasks of the platform will be run. For example, the analytics with the Spark and the supervisors. Well, it's time to focus on the architecture of the solution. Let's start with a 1,000-feet overview of the platform, where you have here in the left part the real supervisors emitting operational data. That operational data goes through Traffic and then reaches the Cloud Supervisors. After reaching the Cloud Supervisors, the data goes throughout the message bus, and it is ingested in Spark. After going through Spark, finally, the data is stored in Hadoop. Well, let's start out the platform components architecture. Well, for the Cloud Supervisor, we have built a Java web-based app with the Spring framework. We have used the dynamic port binding via Marathon because in MESOS, you don't care about what node in your platform, what server. You just, I want to launch my app with one CPU and 500 megabytes of RAM, and you don't care more about it. We use C groups as containerizer for this kind of apps because we don't think that for Java apps is necessary Docker, because with Java, usually the dependencies are inside your application. For the entry points, we use the traffic levels. That is, when we launch the task in Marathon or in MESOS, we assign some labels that will be used for traffic for specifying the entry point for that supervisor. And you need to be care of two things when you use when you deploy Java apps in MESOS. You need to look for first a random number generator instruction. If you launch many tasks in the same node, maybe you need to take care of this thing done in the Java virtual machine. And of course, you will have also, you need to deal with the Java DNS caching. And that is, you need to tune up your Java virtual machine to not catch DNS entries. Sorry. Well, let's start. The only difference between the real supervisor and the Cloud Supervisor is that instead of doing writes in the local file system, the Cloud Supervisor has a Kafka producer module. This module sends data to Kafka instead of the local system in the real supervisors. And in case of connectivity problems, we have a local QB for saving the data. Well, in order to distribute the topics in Kafka, each supervisor just sends data to its own topic. Well, about Spark. Well, we have, as I said earlier, we have deployed Spark using Spark MESOS scheduler. We have here the quite common Lambda architecture where we mix recent data, real-time data with patch. We use here Spark to do data ingestion and storage from Kafka. And we have done, like in the real supervisors with the DDS format, we simulate this standard, the IC 61850, in order to model the data. We have tested the performance of the ingestion up to 100,000 events per second in our platform. And well, this will be the entire flow, data flow from the Cloud Supervisors. First, it goes to Kafka. Then Spark, we do a lot of things in Spark now. First, we will retain recent data on memory because performance, if you have a lot of small files on Hadoop, the performance is horrible. You need to have compacted data. Spark is also used in order to persist operational data to HDFS. We have two tables in order to query the data via a standard SQL endpoint. We have one for recent data and one for the batch data. And moreover, in order to do a normal and easy operational of the system, we have deployed, built, and REST API. Well, let's talk about recent data, the real-time data. We have, as I have already said, we have a recent data in memory table where we can apply real-time algorithms and where the data is saved to the staging HDFS directory. That directory is not compacted, it's uncompacted. And we use the partitioned Parquet with the date and supervisor partitions. Then we have also the batch data, and that is the data at rest. And we expose that data in an old data table, and we change and reload that table when we finish the HDFS compaction. And more of this now. This is the last component of the architecture. In HDFS, you need to avoid small files at all costs. But how we solve it? For this problem, we have scheduled a task executed by Kronos. Kronos is the cron of MESOS. It's a framework for doing cron tasks. With cron and the Kite project, we have used this this Cloudera project in order to do the compaction and move the uncompacted data to the compacted folder. And then we will trigger a Spark batch table reload. Well, let's talk about some conclusion and future work. This solution has been already deployed in three warehouses, and is deploying more and more nowadays. And it's already valuable for the clients, the thing that we can do remote maintenance. For example, you can say to your client, OK, restart this component because it's broken, or it's shut down, or whatever. We have a global data correction available 24/7. And we have a platform that we can deploy easily on any provider. We can on-premise or on cloud. Another point is that we have efficient resource usage of the computing power, and this is a good thing for cost reasons. And the final point, is that we can do analytics and rating and batch data using standard SQL and standard SQL tools. As future work, we would like to move to the DCOs, the open source one from MESOS in order to have more close the commercial support. And we also want to do it because you have tight integration between components. For example, in the DCO system, you have a service discovery tool integrated in the platform. We would like to start doing real-time analytics, for example, anomaly detection for the warehouses. We also would like to evaluate Cassandra as backend storage in order to forget the small file problems in HDFS. And in the future, we would like to have a look to the Spark 2.0 and the structured streaming and dynamic allocations, because with the structured streaming, we will have only one view of the data. We won't have both rating and real time. Moreover, as we have built the platform, we would like to run more ULMA software in the platform, not just the supervisors. And the last point is that in order to forgive the thing that you need to check the SRB DNS records for discovering the ports in the tasks of MESOS, we would like to use overlay networks. That's the point that you will have one IP per task, instead of having a DNS entry with a random port. And well, this presentation has come to an end, and I will be glad to answer those questions that you may have. Thank you.